Welcome to clickmyproject.com. We are going to see the product for built-in self-test and digital calibration of 0IF RF transceivers. Next, we are going to see the abstract for our product. The low-power programmable generator capable of producing pseudo-random test patterns with desired doggling levels and enhanced fault coverage gradient compared with the best-to-date built-in self-test based pseudo-random test pattern generators. It is comprised of a linear finite state machine, a linear feedback shift register or a ring generator is the finite state machine, driving an appropriate phase shifter, and it comes with a number of features allowing this device to produce binary sequences with pre-selected doggling activity. The method automatically selects several controls of the generator, offering easy and precise tuning. The same technique is subsequently employed to deterministically guide the generator toward test sequences with improved fault coverage to pattern count ratios. We propose LP test compression method that allows shaping the test power envelope in a fully predictable, accurate, and flexible fashion by adopting the Presto-based logic BIST infrastructure. The BIST is a design for testability technique that places the testing functions physically with the circuit under test. The test pattern generator generates the test patterns for the CUT. Examples of pattern generators are a ROM with stored patterns, a counter, and a linear feedback shift register. The logic built-in self-test, originally developed for board, system, and in field test, is now gaining acceptance for production test as it provides very robust DFT and is used increasingly often with test compression. This hybrid approach seems to be the next logical evolutionary step in DFT. It has potential for improved test quality. It may augment the abilities to run at speed power aware tests, and it can reduce the cost of manufacturing tests while preserving all LBIST and scan compression advantages. The conventional scan-based test hybrid schemes, due to the high data activity associated with scan-based test operations, may consume much more power than a circuit under test was designed to function under. With overstressing devices beyond the mission mode, reductions in the operating power of ICs in a test mode have been of concern for years. Full toggle scan patterns may draw several times the typical functional mode power, and this trend continues to grow, particularly over the mission mode's peak power. This power-induced overrest may result in thermal issues, voltage noise, power drop, or excessive peak power over multiple cycles, which in turn cause a yield loss due to instant device damage, severe decrease in chip reliability, shorter product life. The BIST can keep average and peak power below a given threshold. The test power can be reduced by preventing transitions at memory elements from propagating to combinational logic during scan shift. This is achieved by inserting gating logic between scan cell outputs and logic they drive. During normal operations and capture, this logic remains transparent. Gated scan cells are also proposed. A synergetic test power reduction method uses available on-chip clock gating circuitry to selectively block scan chains while employing test scheduling and planning to further decrease BIST power in the cell processor. Next, we are going to see the flow diagram for our product. The advantages of BIST include the capability of performing at speed testing, very high fault coverage, elimination of test generation effort, and less reliance on expensive external testing equipment. The BIST techniques are classified into offline and online. Circuit under test. It is the portion of the circuit tested in BIST mode. It can be sequential, combinational, or a memory. Their primary input and primary output delimit it. Test pattern generator generates the test patterns for the CUT. It is a dedicated circuit or a microprocessor. The patterns may be generated in pseudorandom or deterministically. Multiple input signatures register is designed for signature analysis, which is a technique for data compression. MISR efficiently map different input streams to different signatures with every small probability of alias. MISR are frequently implemented in built-in self-test designs in which output responses are compressed by MISR. A quest to achieve higher BIST fault coverage with shorter test application time generated an immense amount of research. The pseudo-random test sequences were modified either by placing a mapping logic between the PRPG outputs and inputs of a circuit, or by adjusting the probabilities of outputting zeros and ones so that the resultant vectors capture characteristics of test patterns for hard to detect faults. We use multiple architecture for the 16-bit output result. Finally, we are going to see the output for our product. Click on the BIST project icon. We are using Xilinx 4.2 version for our project. So we have created BIST project. For creating the new project, click on the file option and click on new project and specify the path that you want to save the project. Then again click on the project, the new source for the program file. It will be created and the program file will be added to our project. For the simulation, we have to click on the simulation and then simulate behavioral model. We will see the output in the iSim. Here we have to give the reset value as initially 1. Then give the clock value. Leading edge value is 0. Trailing edge value is 1. And period is 1000 nanoseconds. And click on the run option. Then again click on the RST and force constant value is 0. Then again run. It is the address and this is the corresponding data. If there is any error occurs, this 0 will be turned to 1. Click on the run. So the address changes and the data also changes. There is no error occurs. When there is error occurs, this will be 1. Minimize the iSim. For the implementation result, click on the implement and implement design. Here implementation design is already implemented. So click on the synthesis report for the number of flip-flops and LUTs used. So number of slice registers 33, number of slice LUTs 130. So this is the synthesis report, HTL synthesis report. We have to click on the advanced HTL synthesis report to view this. Then for the timing report, we have to click on the timing report. Here the programming time is 2.336 nanoseconds. To view the RTL diagram, we have to click on the synthesis XST and view RTL schematic. Click on OK and then add create schematic. Here double click on the diagram and the logical diagram will be shown. Thank you.